Hello everybody. Welcome to ComSci Connection, Recursion Example number 1. Today we're going to talk about, recursion. I just told you that, and it's going to be pretty simple examples. We're going to kind of explain the basics of it. There's a little bit of information in the topics, obviously, but this is going to be kind of a more visual example. One of the best ways I can think of to explain recursion would be to take a box. This box, for example, we're going to talk about what you do with a box, right? I mean, why do you put something in a box? Maybe to protect it, maybe to keep multiple items. But one way or the other, a box contains things. It has something inside of it, some content, or at least we hope so, that is of value or of use to someone or something. As the receiver of a box, you don't really care about the box itself. I mean, it's nice that it's there, it serves a purpose, but your intent is to get to what's inside the box. You want to open that box up and find out what you've been given. So we're going to do that. We're going to take this box and we're going to open it up. But inside, we find another box. So that's weird. But nothing's really changed. I mean, we still have a box, right? And our objectives are still the same with it. In fact, everything is the exact same except for maybe the size. We still want to open the box, so we're in other words going to repeat the same steps that we previously did in order to complete the same goal. Nothing has really changed. So let's go ahead. We're going to open that box too and find another box. So again, nothing's changed except for the size of the box, but we still have the same goal and we still haven't reached it. So since we can identify that as humans, we're going to go ahead and open the box again. And you might see this coming. There's going to be another box inside. So at this point you say, all right, over the fact that this is strange, let's just continue on, and you get to an envelope or something. So basically, as you've noticed, we repeated several steps over and over and over again. And we followed the same set of instructions. We looked at what we had in front of us and identified whether or not it was our goal or not. And if it wasn't, regardless of which step we were on or how many previous steps had already taken place, we completed the same set of events. And this is in essence what recursion is. This box here, for example, at this stage doesn't care that it was actually the content of 3 other boxes. All it knows, and all you know being the person that has the box, or if you were to think about it in a computer's terms, the method given the object box, what do you do with it? It's still the same thing you would always do with it. You look at it, you say, this is not the goal, so I'm going to proceed doing the same thing until I get to the goal. In this case, an envelope. Now, what if I told you that I had 100 boxes that I wanted you to open, and every single one of them may have a different number of boxes? I might give you a box that has only one box, and then the object is right inside of it. Or I might give you just the object directly, or I might give you a box that has 1,000 boxes. You want to write, as a programmer, one stage or one set of, one series, that's a better word, one series of instructions that regardless of how many boxes are contained inside other boxes, you're always going to end up with the end result. And I'm going to take it one step further, and I want you to tell me, giving you each box one at a time, I want you to perform the same set of events and tell me how many boxes you had to open in order to reach the goal. So a little bit of return magic. Now, if you think about a typical function, you know that, let's say I want to take the square root of 25 and I want to add 1 to it. Now, you might have done this, you might have seen something similar to this, but you say, let's just say that we're going to print it out to the screen. I say square root, I call the square root function from the math library, square root 25 plus 1. Well, you just kind of run it and you see it happen instantly, and you might just think, oh yeah, well it just worked. I mean, it just got the square root. But what really happened there? I mean, what it really did was it referred to this math library, often in some other code somebody else much smarter than me wrote a long time ago, and it takes in this value that you provide, in this case 25. It calls that function. Your code stops completely, and it sits there and it waits. And it says, I can't do anything else until I receive the answer back to this question that I've sent off somewhere. What is the square root of 25? I don't know. Well, the math library does know, and so it refers to the square root function, takes in 25, performs some crazy series of events, and then returns a value 5. And then that 5 is given back to the function, to the place where the function was called, or it's returned, which this shouldn't be blowing your mind. But this value 5 is now available to me and something I can use. Now I have 5, and I can say, oh, 5 plus 1, well, that's 6. And then, oh, great, I print 6 to the screen. Recursion is kind of similar. If I hand you this box here, and I say, tell me how many boxes are inside this box, or tell me how many boxes there are total, you really know that you're going to open a box one at a time and add and count one at a time until you reach the end goal. So you can write a recursive function to do the same thing. You can say, start out with what we call a base case, which is saying, what is our goal? Well, our goal is, whatever the object is inside. I'll just refer to it as the goal. Well, are we at our goal? No. So what we're going to do is go ahead and we can assume, or we know, that it must be a box if it's not the goal, at least in this example. It must be a box. So we can go ahead and open the box and then count 1, right? So we do that, and we open all these boxes, and we get to the end result. So if it's the goal, that we've reached the goal, and we don't need to open any more boxes. So we can take this and say, well, I don't have any boxes, and I can give an answer, 0, if I was given like an object directly. Think about this like an assembly line. Each one of these is given the task to determine how many boxes it has given to it. This box would eventually need to answer 4, right? This one would answer 3, this one would answer 2, but at this stage you don't really know. It's just a box. It has some mystery behind it. When you are at this stage, you know that it's this stage here. You know that it's 0 boxes. So our end result, or our goal, can return an answer 0. Think about it like an assembly line. The person on the far right that gets the right answer, finds the object, can say, oh, can turn to the person to the left and say, I've got 0. And that person can say, oh, great, you had 0. Well, I had 1, so I'm going to add 0 to 1, and I'm going to send the answer 2 to my left. And then that person can take 2, or did I say 0 plus 1 is 2? Is 1, and then 1 will be taken in by that person, and he'll say, well, actually, I'll show you. So the person who receives the object will send the answer back, oh, 0. Well, 1 plus 0 is 1. And then that person will say, oh, well, you say 1. Oh, great. Well, I opened 1 as well, so I'm going to add 1 to 1 and send 2. Well, that person will receive 2 and say, oh, you said you opened 2 boxes. Well, that's great. I opened 1, so I can do that. And if you notice, every time we're just adding 1 because we made one call saying, I took 1 box and I kept it, and I handed the contents of that box to the person to my left, and then they looked at it and said, oh, nope, it's a box, and they sent it to their left. And eventually you're going to end up with the final answer 4. It gets back to the place where it was originally called, where the function was originally sent out and said, I need to know how many boxes are here, and it comes back with 4 eventually. And that is the magic of recursion. You basically have to assume that you can look into the future. You can say, well, if I opened a box, then I can say whatever answer this person to my right gives me once I hand in this object and wait for the answer. Whatever answer they give me, I'll just add 1 to it and then pass that back. And this is basically the domino effect of recursive calls falling off the stack and sending answers back until you end up with a final answer. So enough of my terrible imagery. Let's actually look at a specific example in code. Now I hope that this is easy to read. I tried to make it large enough to be read. If not, then I probably will just spice this part out. But we're going to start with a factorial example. So if I say I want to find out the factorial of 10, if you don't know what a factorial is, it's simply just 1 times 2 times 3 times 4 up to 10, or if I was doing it, factorial of 2 would be 2, 1 times 2, right? Factorial of 10 is 1 times 2 times 3 times 4. Well, that's much harder. I can't just do that mentally. So what I do is I determine, well, I know what the factorial of 0 is, right? It's what is it, 1? Actually, yeah, it's 1 for some reason. And the factorial of 1 is also 1. So I can define that as my base case in my function called factorial call here. I say if the number I'm given, which it takes in as an argument, is 0, or if the number is 1, then I just return the answer 1. In other words, I've reached my goal and I know my answer. If it's not, and it should be obvious here that if this line executes, then this code won't ever execute. So I didn't have an else statement here, but I could just as easily have written else here and done that, and that's fine too. But in fact, I'm going to undo that because I like being fancy. So we're going to watch this happen. So it's going to call factorial call with 10, right? And we're going to step over this. Nope, excuse me. We're going to step into this so we can watch it happen. So at first it's going to take in the number 10, right? It has a variable called 10. Here it is on the stack. We've got main, which is still sitting here waiting. It says I asked for the factorial of 10. I haven't gotten an answer back, so I'm just going to sit here and wait. Factorial call takes in the number 10, has a variable called number, which has the value 10, and sits here on the stack above main. Main can't continue until this completes, until this call completes and it gets back to this point. Well, it's going to evaluate, oh wait, factorial or number 10 is not 0 or 1, right? So I'm going to go ahead and return the number 10 times the result of factorial call of number minus 1. So that would be 9, of course, right? So if I step into this, I'm going to see that it just seems to have jumped backwards, and you might be a little confused if you've never seen this before why that happened, but it didn't actually jump backwards. If I click on the lower level stack, you see that it's still right here. It's still waiting on this line because it's saying I have number, that's 10, and it even will tell us right there number is 10, but it doesn't know what this is yet, and it can't do anything. It has to sit and wait. It has to wait, has to look into the future and wait for that answer to come back to it. A new level of the stack was created here with number, the same variable number, but it's different because it's on a different stack. So it's a different element on the stack, so it has a different value for each one of the variables. It might be confusing that that number is 9 where this number is still 10, but in fact it's going to follow the same number of events. It's just another box inside of our box. So we're going to say, is 9 equal to 0 or 1? No. So I'm going to go ahead and return 9 times the answer of factorial call of 9 minus 1, which in this case is 8, right? Step in, look, another element has been created on the stack with number variable equal to 8. It's not going to be equal to 0 or 1, so we're going to return 8 times the factorial call of 1 less than that, 7. Now, I'm going to keep going here a little bit, and we're going to skip over because you should be getting the idea of how this is working, but 7 will 6, 5, 4, 3, 2. Now before I go on, I'm going to show you the stack here. Main is still sitting here waiting. Main is still saying, hey, I asked for the factorial. I don't know where this guy is, but he hasn't come back yet with my answer. So it's not my fault. Don't blame me. I'm just going to sit here and wait. I don't care. This guy is still saying the same thing. I asked for the factorial of 9. I haven't gotten it back yet, so I can't do anything. But once I do, I know I take that and I multiply it by 10 and I send it to that guy. And this guy and this guy and this guy, all these guys exist, and they all have the same variable number, but it has a different value on every level of the stack. The same with this guy. He's going to say 2 is not equal to 1, but it is, and it's not equal to 0, so I'm going to go ahead and take 2 times factorial call number minus 1, which is going to be 1, and this time we've reached the goal, right? We know that we were at the base case, and we can return an answer. Number equals 1, well 1 can't, there's no factorial for 1, it's just 1. So I just return 1, which will watch as this element will disappear off the stack. This one's still here waiting, but this element will disappear off the stack. It'll say, yep, return 1, great, disappear. Now I'm back to 2. Well, now this is going to take number 2 times, you can't see it, but this answer has been returned here as 1. Well, 2 times 1 is, of course, 2. So if I step over, that's going to fall off the stack, and now I'm back to this period. So 2 times 3, 6. That's going to fall back here. You can't see it, but 6 exists right here, and it's going to multiply that by 4, 24. We're going to keep going in the same sense. Multiply that by 5, multiply that by 6, multiply that by 7. As the answers fall back, the dominoes are falling back over, and they're returning the answer to the person to their left, just like our assembly line. We're going to come back, all of a sudden we're at whatever the factorial of 9 is, times 10. This guy goes, oh, finally, man, where have you been? I finally take your answer, multiply it by 10, and send it back to this guy over here who's been badgering me for the longest time. And we can do that, And then finally it's going to say print out the factorial of 10, which when I step over we will see is, what is that, 3,628,800. Isn't that fascinating? It doesn't mean anything, but it should let you see exactly how this works on different levels of the stack. You know that you have a problem that you can follow the same series of steps on over and over and over again until you get an answer. Until you reach something that you can work with, you can continue to break that problem down into a simpler and simpler problem until you've reached some kind of base scenario that you can work backwards off of. And you basically just call the same function over and over and over again internally. It's completely against everything our English teachers ever taught us. You know, you should never define a word inside, or you should never use a word inside its own definition. Well, this doesn't follow those rules at all. In fact, recursion is an excellent tool when used properly, and you will run into situations in your future where you have no other choice, where recursion is the only real way to do it. And if you don't use it in the right situations, in other cases it can severely cost you. So hopefully this video has been helpful. There are going to be 2 more examples up as well, so good luck, and let us know if you have any questions.